Hi class, I am Michelle Hsu. I am part of Statistics Without Borders team. It's my honor once again to be part of the African Institute for Professional Development instructor on the classification class. And this is the continuation of our prior part 1 lecture. So if you haven't watched the lecture, it is available as part of this series. Before we get started, a little background about myself. I am a statistician by training, and I hold a master's degree in applied biostatistics from Boston University School of Public Health. I work for a CRO, which stands for Contract Research Organization, and I lead and support various indications of clinical trial studies for pharmaceutical companies. So for today's class, if you have any questions, feel free to reach out and send email. I do have the email here listed on the slide. Next, as part of part 2 lecture, we'll be covering classification accuracy agreement, measure of association, and precision and recall. And again, we'll be looking at categorical outcomes as opposed to continuous or discrete outcomes. Classification accuracy and agreement. Right, so when we handle binary outcomes and evaluating agreement between the two variables on a comparable scale, we can look into sensitivity, specificity, positive and negative predictive values, which were actually covered in our prior lecture. So today we could actually also look at the proportion or percent in agreement. And that's what we're going to cover under this session. So when we evaluate the classification rule to determine whether the performance is accurate or not, we can calculate accuracy as a metric, which is simply the proportion of observations that have been correctly classified. In other words, from a machine learning perspective, we say that accuracy corresponds to the rate of correctly classified labels in the test set, right? So if you look at here, I have the formula of the accuracy. So you see that the numerator is simply the sum of true positive and true negative, and the denominator is simply the sample size, right? So it's accuracy then it's easy to calculate and intuitive to understand, making it almost the very common metric used for evaluating classifier models. What I don't have here on this slide is the classification error rate, which is simply the proportion of observations that have been misclassified. So let's look at an example in our next slide. So here I have an example, a confusion matrix displaying columns of disease status, showing disease and not diseased, and rows of screening tests showing positive and negative. So as you can see, the diagonal elements of these confusion matrix indicate correct predictions, while the off-diagonal represent incorrect predictions. So the correct classification rate, we follow the formula, is the sum of the number of the diagonal divided by the sample size here. So we have true positive plus true negative, which is 91 divided by sample size of 100, which is 91%. Now, the reason why I'm giving this example is that you can actually see that we have imbalanced data here. So, and this is actually very common if you work on the rare disease clinical trials. You'll see some kind of variables or some measure of absence and presence of a rare disease. So it's likely that almost all of the samples will have negative for both of these disease status and screening test values. So in our next slide, we'll be cover what it's called a measure of agreement, kappa, or Cohen's kappa, which adjusts for how much agreement by chance you would have here. Next slide. Now, when the outcome is binary in or nominal with 3 or more groups, we can use Cohen's kappa and calculate kappa statistic. So the Cohen's kappa was developed back by Jacob Cohen back in 1960, and it's really the measure of agreement, and it's symbolized by lowercase Greek letter k. It's just for how much agreement by chance you will have. So it measures inter-rater reliability and statistical classification reliability. Like most other correlation statistics, the kappa can range from -1 to +1, right? So -1 means there's no agreement, +1 means there is a perfect agreement. So Cohen's kappa is a robust statistic useful for scenarios where data is imbalanced, right? So to look at an example here, you can see that we have a reference table from McHugh's 2012 paper, and the formula for K is by taking the difference between the actual observed agreement and chance agreement divided by 1 minus chance agreement. So if you want to use that example that we have from previous slide, you can notice that we have PA percent agreement equal 91%. And to calculate PE, you take the disease and positive number of cases with 100 plus 91 times 98, meaning that we're taking the non-disease and negative cases, divided by 100 and divided by total sample size, you get 89%. So to calculate a K value here, you would have 0.18. So to go back to the prior table reference, 0.18 is equivalent to almost non-level of agreement at all, meaning that only about 0 to 4% of the data are actually reliable. Now, indeed, by just looking at the example, you can note that the kappa was designed to take account of the possibility of guessing, but there are assumptions also, right? So the assumptions makes about greater independence and greater other factors that are not well supported. So that may lower the estimate of agreement excessively. And it cannot be, it's hard to have a direct interpretation. And so it is actually quite common for researchers to accept low kappa values in their inter-rater reliability studies. So the best advice is to calculate both the percent agreement and kappa. Now, next slide. When the order does matter in the data, we have another method to use, which is called a weighted kappa. So weighted kappa is a version of kappa used for measuring agreement on order variables, where certain disagreements, for example, lowest versus highest, can be weighted as more or less important. So when the ordinal scale variable is for disease activity, for an instance, with levels non-moderate and severe, weighted kappa does it that it would not say rating non and severe is as bad as having them say non and moderate. So when the scales are ordinal, weighted kappa weight the discrepancies so that those ratings, the more discordant, are considered worse. In other words, when computing kappa statistic, that's done so by that the more discordant are given less weight in computing agreement. In this slide, you can see the weighting scheme here. So the weighting schemes can be formulated from either a similarity or dissimilarity perspective, right? So to compute weighted kappa, weights are assigned to each cell in this contingency table, and the weights range from 0 to 1. 1 assigned to all diagonal cells. And again, when K is 0, the agreement is no better than would be obtained by chance, right? So weighted kappa can be calculated by plugging this PA, sum of weighted proportions, and PE, sum of the weighted product of rows and columns of marginal proportions. And in many instances, the researchers would also want to determine what type of weights to use. For example, there are linear weights, meaning that each weight is at equal distance, equal spacing between them, or quadratic weights, right? So if we're using linear weights, that means the difference between the first and second category has the same importance as the difference between the second and third category. Or some researchers might say I want to use quadratic weights because the difference between the first and second category is less important than the difference between the second and third category, right? So I think the most important key takeaway here is that variables could actually be highly correlated without agreeing with each other, right? So the two measures would be highly correlated but would not agree with each other because one method can consistently be higher than the other method. Next, measure of association. Measure of association, Kramer's V. And now you might ask, what's the difference between chi-square test and Kramer's V? So chi-square test is a measure of statistical significance, and it answers the question, is there a relationship between our dependent Y variable and our independent X variable, for example? Whereas Kramer's V is a measure of substantive significance, and it answers the question, how strong does the relationship appear to be? Right, so here on this slide, Kramer's V is used to measure the strength of an association between two nominal variables. It may be used with variables having two or more levels. It is developed by a Swedish statistician, Harold Kramer, in 1946. It is derived from the Pearson chi-square statistic, and it is useful for comparing multiple chi-square statistics and the generalizable across contingency tables of varying sizes. And indeed, it does not affected by sample size, and therefore it's very useful in situations where you suspect a statistically significant chi-square result, but possibly the result was due to large sample size instead of any actual substantive relationship between the variables. Right, if you look on the slide here, Kramer's V is the square root of chi-square test divided by total sample size times number of, either the number of rows minus 1 or number of columns minus 1. And one important key also is that correlation is not the same as agreement, right? So that any analytical method used for either depends really on the scale. Next we have precision and recall. Precision and recall are important measures for classification and diagnostic testing. Now you may ask, what's the difference between these two measures, right? So now let's focus on precision first on this slide. When we work with precision is concerned with the fraction of true positive and all predictive positives, right? So precision is equivalent to positive predictive value, which we briefly covered in our session 1. And if you look at the formula, precision equal to TP, true positives, divided by sum of true positives and false positives. So precision would tell what fraction of the identified cases actually are positive. And if the model gives 0 true positive, that means precision is 100%. So suppose we correctly identify 1 true positive, here in this example table here, and incorrectly identify another one false positive, our precision would be 1 divided by 2, which would give 50%. So it is 50% correct to correctly identify a patient who has a disease is actually also positive. Right, now we move on to the slide here. Let's focus on recall. Recall, on the other hand, is concerned with proportion of identified true positives among the disease population, disease sample. So recall would tell what proportion of actual positives were identified correctly, right? So, and if the model gives 0 false negative, that means recall is 100%. So recall is equivalent to sensitivity, which we also covered in our prior session 1. So using the same example, the model we are using has a recall of 1 divided by 1 plus 8, which is 9. In other words, it correctly identify 11% of all disease and positive patient, right? So I think I have an actual example here. Right, so recall shows how accurate the screening test is in identifying disease in people who truly have the disease. And so when thinking about sensitivity and recall, we want to focus on individuals who in fact really were diseased in this case. The left column is the denominator. So to fully evaluate the effectiveness of a model, we should examine both precision and recall. Great. So to summarize today's lecture, we have 3 reminders and key takeaways. Number 1 is the interpretation of classification accuracy in the agreement, and correlation depends on the variable scale and possible outcomes. And variables could be highly correlated without agreeing. The 2 measures would be highly correlated but would not agree with each other because one method can be consistently higher than the other method. Number 2, correlation is not the same as agreement, and that the analytical method used for either depends on the scale. Number 3, there is a reverse relationship between precision and recall. So precision answers the question, what proportion of positive identifications was correct? Whereas recall answers what proportion of actual positives was identified correctly. And that's all. Thank you very much for watching, and then feel free to send me any questions via email.